So I'll talk today about modeling the built environment for the exposome. I'll give a short outline of the talk. I'll start with a brief introduction about modeling, then move forward to discuss new advances in PM 2.5 and PM10 air pollution modeling. Later, we'll discuss spatiotemporal air temperature modeling, and finalizing by discussing geospatial built environment modeling. So as we saw yesterday by the great talk from Dr. Sorek-Hammer, there's a lot of satellite data available, and it's increasing every year. And I'll give a brief introduction to the satellite-based modeling methods for environmental epidemiology. So why do we model PM 2.5? Why do we model temperature? I'm sure everyone sitting in this room is well aware of the extensive literature on the association between PM 2.5 and health outcomes, which include hospital admissions, mortality, reduced birth weight, cardiovascular disease, respiratory disease, heart attacks, and a lot of other health outcomes that have been extensively researched. Changes in climate will also lead to warmer temperatures and more extreme weather events, which are associated with increased morbidity and mortality in sensitive populations. This increase happens not only during heat events, but also in less stressful or less extreme heat events, and we've published on that in an EHP paper in 2015. I want to present some of the modeling approaches that we've been using over the past years to assess robust exposure for health studies. Traditionally, people have been using proximity-based assessments, that is, what is the distance to a major roadway, to a point source emission. We've also used interpolation techniques such as kriging and IDW, using existing monitoring networks. Further to that, we've started implementing more advanced methods such as land use regression models, line dispersion models, but we've moved or shifted towards using hybrid models in recent years, and that's due to limitations of these previous models. First of all, they tended to use large geographical areas such as state or nationwide resolutions, and thus potentially biasing the health effect risk estimate due to exposure measurement error. And also, a lot of these models use monitors which are focused on urban areas because the monitors are located there and the population is centered around these urban areas. To avoid these limitations, we started developing new hybrid modeling methods to incorporate satellite data. We've heard yesterday of the advantages of satellite data, their broad spatial extent, enabling us to expand our exposure data and exposure modeling beyond the range of conventional ground monitoring stations, and greatly enhances our ability to estimate subject-specific exposures. These measurements, collected daily or sometimes intradaily with varying resolutions, can help us robustly reconstruct personal exposure at a higher spatial and temporal resolution. Some of the advantages that we heard of yesterday were the great spatial coverage. You can cover the globe. You can survey areas with very limited ground monitoring access, such as Africa and parts of Asia. It's very economic. You have one sensor covering the globe. But there's a lot of disadvantages or a lot of limitations. We have issues with data availability. If there's snow, if there's cloud coverage, if there's a dust storm, we don't get satellite data. You've heard that there's not a lot of satellites that deal with vertical profile, so we have to take the whole integration of the atmospheric column into account. And there's different spatiotemporal resolutions that we have to deal with. In order to deal with all these limitations, we started looking at robust and advanced methods to model air pollution. And I'll present some of the modeling approaches that we've used over the last few years. So the main satellite that we've been using is the MODIS satellite, the Moderate Resolution Imaging Spectroradiometer. It's a satellite comprised of it's a system comprised of two satellites, the Terra overpassing in the morning and the Aqua overpassing in the afternoon. Each instrument has 36 spectral bands at varying spatial resolutions, And the main products that we incorporate into our modeling efforts are AOD and LST, which is land surface temperature. This is an example, I don't know if I have a pointer here. This is an example of how the raw image coming from MODIS looks. This is the AOD product that is derived from these images, and there's different algorithms to process the images into AOD. There's a dark target algorithm, which is very useful over dark surfaces such as oceans and specific land types. There's a deep blue algorithm, which is developed to address very bright surface areas such as deserts, and the MAIAC algorithm, which is a combination of both of them. The MAIAC algorithm, the multi-angle implementation of atmospheric correction, is an algorithm developed by PI Liapustin, which we have a close collaboration with since the onset of the project. It provides higher resolution AOD at a 1 kilometer resolution, and also very robust AOD measurements performing well over different surface types. AOD, just to refresh everyone's memory from yesterday, or aerosol optical depth or aerosol optical thickness, measures the light extinction by aerosol scattering and its absorption in an atmospheric column. It's a unitless value ranging from 0 to 3 and above. This is an example of an AOD day which is polluted over India, where we get values of 0.4, and this is a very cloudy day over Brazil, which corresponds to high AOD values. So how do we do this? How do we get from AOD to actual predictions? We have developed a methodology that takes these daily AOD HDF raster images from MODIS and MAIAC, and then we process that through a series of algorithms and tools that we developed. This is an example AOD day over the Northeast, where warmer colors correspond to higher AOD levels. And then we have developed packages which are freely available in GitHub called NNGeo and AOD LUR, which allows us to spatially temporally link the AOD data with monitoring stations on the ground. This is done because the monitoring stations are fixed, but the AOD data changes day to day in location usually. We then supplement this with a very extensive spatiotemporal database, which includes land use data, metrology data, atmospheric data, and so on, and build a very rich data set that includes, traffic density, planetary boundary layer data, temperature, and so on. Once we have that, we can start calibrating the model. And the way we do this is quite simple. We start with a calibration stage. We talked about how AOD is in this column of air, but we're interested on the surface level about what people are breathing. So we incorporate these spatiotemporal variables to calibrate the AOD data with PM. This is our first stage, where we regress the PM data versus AOD data and the spatiotemporal predictors. Once we have this relationship, we can go on to areas that we don't have PM stations but do have satellite data and predict to these points. Because we're interested in predicting towards environmental epidemiology studies, we want to take a look at both the acute and the chronic exposures. We want to have daily prediction, which is what differentiates our model from other models. We have a third stage, which is a stage where we regress the AOD from the stage 2 versus interpolation of localized PM monitoring stations plus a thin plate spline, which allows us to predict daily at every point and every day. Additionally, in recent years, we have another stage, a fourth stage, which we call the local PM stage, where we take the residuals of this long range or local PM data that we predicted, and we predict high resolution PM at a 100-meter resolution. I'll show that in a second. In mathematical form or notation form, we have the first stage, which is the calibration stage. We used to use mixed effect modeling. Now we've moved towards machine learning approaches, which I'll present. But in essence, we regress the PM at day J at monitoring station I versus AOD, the temporal and the spatial predictors, and a random intercept for day and a random slope for AOD. This is followed by our third stage, where we regress the PM predicted in second stage at grid cell I at day J versus the mean interpolated PM from the monitors and the thin plate spline that allows us to borrow information from adjacent cells. Finally, in the local stage, we run machine learning methods to take the residuals and regress that against high-resolution spatial and temporal predictors. So how does that actually work and how does it look? So we've published a bunch of papers that have been successfully used in a lot of environmental epidemiology studies over the recent years, and I'll present some of them. This is the result from the first model, the 10-kilometer MODIS, not yet MAYAC, over the Northeast, and you can see that the model performed quite well initially, both in the New England area and the Mid-Atlantic region. We also wanted to see how does the model perform in other regions with a different pollutant, PM10 in this case, and we published a study in northern Italy. And this is the 2014 paper where we moved over to using MAYAC data as opposed to MODIS data, and you can see the higher resolution, you can see the variability within the city, you can see the differences between the rural areas and urban areas, how the model is able to capture road-based particles, and the spatial temporal variability of the model. These are the result of the aggregated 1-kilometer grid cell across the year 2003. When moving over towards the local stage, we're predicting here at a 200-meter resolution. I overlaid the road network and the point source emissions from the EPA, and you can see how the model is able to capture variability and really track the point source emission over Boston. Model performance was also improved. We're looking at predictions around 0.9, cross-validated, slopes of 1 showing no bias in the model, and great spatial and temporal performance. So it's all fun and nice, and we love modeling, but we have to do something with the data. To show that it's actually relevant for studies. So we conducted a study looking at short-term effects of particle exposure and hospital admissions in the Mid-Atlantic states. We know that many studies showed significant associations between PM exposure and hospital admissions, but these studies rely on a limited number of monitoring stations, which obviously introduces exposure error and excludes the rural and suburban population, which is a critical point. And then that reduces generalizability and potentially creates selection bias. Using our prediction models, we investigated the short-term effects of PM2.5 exposures on emergency hospital admissions of the elderly in the Mid-Atlantic region using the Medicare data. I put this figure to show how usually studies are done. If you have monitoring stations, you usually create buffers around them. The monitoring stations are denoted as black flags. And I created these buffers of 30 kilometers to show how some studies that don't have access to these new hybrid models or spatiotemporally resolved models assign exposure. And I put a buffer of 30 kilometers, even though we know that that's really too crude to be used in study these days. And you can see that a lot of the population is excluded from the actual study, a lot of the Medicare population. By using a spatiotemporally resolved model, you can include the whole of the population and robustly assign exposure to every single person within the study. So we did that. We used a case crossover approach, commonly used, matching on day of the week, month, and year, defined a hazard period of lag 0.1. That is a moving average of day of admission and exposure of the previous day. And we found significant associations with all respiratory, CVD, stroke, COPD, and IHD admissions. So that's all great. We've heard yesterday that satellite data are global. I finished my postdoc, and I thought, yeah, let's just model the whole world. It's very easy, probably. Use the same approach. Very quickly, reality hit. And unfortunately, there isn't a one-size-fit-all approach, which is, everyone that's done modeling on a global scale knows that. Each region has a very distinct geoclimatic characteristic that presents very unique challenges, such as snow, dust storms, mountains, humidity. For example, in Mexico, where we modeled, we immediately saw that we have issues with humidity and precipitation. The PBL is very low across Mexico City, creating a pressure cooker effect where particles are not able to move freely. A lot of strong wind regimes. In Israel, completely different scenarios. We have a lot of issues with surface brightness and sandstorms. In fact, the MAIAC algorithm didn't perform as well, and a lot of the work done by Dr. Sorek-Hammer, going back and forth with the MAIAC team, allowed them to improve the algorithm to perform better over Israel. And in general, we have much higher annual PM levels. So this is the Israeli model. You can see the distribution of the PM stations, and you can see that we had to develop different methodologies to account for these different geographic characteristics. This is a day of typical sandstorm over the area. This is how it looks if you look outside the window. It's, PM levels are in the extreme. So we had to develop a classification of dust event, and this is also work by Dr. Sorek-Hammer, where we classified which day is a dust event and which one isn't in order to better fit the models. This is the final result of this work in Israel. You can see again the nationwide map of PM10 predictions across Israel with a very high performance, and in addition, the PM 2.5 model across Israel. In a similar way, this is work led by Dr. Just in collaboration with our lab. We developed a model over Mexico City. We wanted to produce daily estimates on a 1 kilometer resolution spanning 2004 to 2014. Mount Sinai and Professor Robert Wright has a very successful and long-standing cohort in Mexico City. Before this model, there wasn't any data available regarding modeling or modeled air pollution. And we successfully developed a model over Mexico City, augmenting the sparse monitors. And this has been used in several publications, and this is the result of this study. I can't put or can't overlay the location of the participants due to IRB issues, but it's around this area, and you can see the sharp gradient in exposure, where if you wouldn't have a model, you would have to assign exposure from a specific close-by station or use interpolation techniques, which would severely bias the estimations. We have additional studies across Europe, across India. We have papers in Italy and Switzerland. We just submitted a Horizon 2020 grant to model air pollution, PM 2.5, PM 10, NO2, ozone, temperature, and traffic across Europe on a 1 kilometer daily resolution and a 100-meter daily resolution for the entire EU 27 now after Brexit. And hopefully this work would start in the next few months. So we've seen how we model PM 2.5 on a daily level, but we have additional ideas on how to move and progress from that. One of the things that we're doing, and we just published a few months ago, was intra-daily PM modeling. We took Israel as a pilot study, and we wanted to estimate PM 10 and PM 2.5 for below the 24-hour daily resolution based on the satellite overpass. We wanted to do that because we hypothesized that in the morning, where the Terra satellite overpasses, the characteristics of the particle is very different than compared to the Aqua satellite in the afternoon. In the morning, the PBL is very low. There's a lot of anthropogenic activity, and thus the particles are different in the afternoon, where the PBL goes up. A lot of long-range particles are coming in, and there's less anthropogenic activity. So we used our hybrid 3-stage approach to do so, and we found some interesting results. First of all, during the overpass times of Terra and Aqua, we saw significant differences in PM concentrations relative to the daily mean concentrations. We saw different spatial patterns of the mean PM for non-dust periods compared to the dust events that we have. And we're starting to use these two different exposures one anthropogenic and the other we call the background exposure in health studies as two different exposures. And these are the results of the model. As you can see, it performs very well as well. And these are the maps, the daily, the hourly, from Aqua and Terra, both for PM10 and PM2.5. The next interesting thing, and this is a paper that was just published a week ago by my student, Alexander Stein, is modeling using an ensemble approach. As I said, different regions have different characteristics and different limitations. It's very challenging to model Italy. There's a lot of, geoclimatic gradients, mountains in the north, Mediterranean climate in the south. And we weren't successful using our traditional approaches, so we developed an ensemble approach. And we innovated in a few key areas. First of all, we managed to predict PM, or to create these daily surfaces of PM. We're using other satellites and CAMS data to create these daily surfaces of AOD, which will greatly enhance our computational efficiency. And then we calibrate, we predict, we take the residuals, and then we have our local stage. The reason that we developed these ensembling approaches is that we felt that every model that we're kind of evaluating has its own merits, biases, and limitations, and ensembling them would give us the best overall predictions. We took a look at 4 different models: a linear mixed model approach, a random forest approach, a gradient boosting approach, and a CTM, a chemical transfer model approach. And we put them inside the model. We went through very rigorous validation, running each model 10 times, over 80% of the data, taking 10% off for training and 10% off for validation. And after we imputed this continuous surface, we took the predictions, run an XGBoost model all the way to get predictions, run the linear mixed effect model all the way to get predictions, ran the random forest to get predictions, and the CTM model, and then put this in a GAM. The reason that we ensemble through a GAM is that we can have the predictions vary both over space and time. So, like the Avengers, each model kind of contributes, and then the overall prediction should be better. And indeed, looking at the ensembling approach, we see that we improve upon every single model individually, both in terms of the overall R-square, the root mean square prediction error, and the spatial and temporal performance. These are the maps of the different models: the GAM, the mixed effect model, the random forest, the XGBoost, and the FAR model. And you can see why we don't really believe in these CTM models and why we kind of model ourselves. You can see the FAR model doesn't perform, the CTM model doesn't perform as well. I think I'll skip this because of time limitations, but we have different approaches to also predict PM robustly in rural areas using a GRF or GRMF approach, where we use Markov properties to enhance the GRF approach. And you can see that the models perform much better as you move away from a monitoring, comparing to the linear mixed effect model. And we published this as well a few months ago, and we're going to incorporate that in our next ensemble modeling approach. Another interesting work that Alan, Professor Just has led is error correction of the AOD data. A lot of the data that we receive from NASA, while great, I don't know what's going on with the PC, but I think the battery is going to die. So I'll talk super fast. So we managed to find a way to evaluate and improve upon the raw AOD data by running an error correction method. We trained 3 separate machine learning approaches on the MAIAC AOD data and AeroNet stations who measure AOT or AOD from the ground up. We decided to use the XGBoost tuned model to basically correct AOD. If you can look at this left image, you can see that there's very high AOD levels, but this is false. This is not really high pollution days or high polluted areas. This is a cloud basically covering the areas. So we managed to correct AOD values, decreasing root mean square prediction error by 44%, and more importantly, the raw correlation between AOD and PM in the calibration stage increased by 10 percentage points cross-validated, which was really impressive. We are also now part of the ECHO initiative. Professor Just and myself got the OIF grant under ECHO to model nationwide or CONUS-wide PM 2.5 temperature and greenness using satellite data, and this would be the basis for exposure variables for over 50,000 children across the US. So we've talked about temperature, about PM, I'll move over to temperature. And when I was starting my kind of career as an assistant professor, I thought, you know, why don't we use some of the methods that we've developed for the PM modeling to model temperature? Temperature is also, you know, an important exposure, and you need spatially resolved temperatures to have variation, to reduce exposure measurement error. There's not a lot of stations always available, especially in rural areas, and the reanalysis data sets that are available are not high enough in terms of the temporal and spatial resolution. So we started looking into temperature, using some of these approaches, looking at hourly temperature measurements from meteorological stations. For example, in New England, we had more than 26 million observations. Looking at MODIS satellite data, which is land surface temperature data, it's a different product, and applying some of the methods that we have developed for temperature. And this is the result of the first model that we published in 2014. We're all in New York now. You can identify this big kind of green area that's very close to us here, which is Central Park, and you can see the spatial variation and the differences between, you know, these yearly aggregated temperature values for each 1 kilometer, and the difference between the kind of Central Park area and the urban core, the downtown area, and these are huge differences. You know, it's 2 degrees and can be extenuated when it's a severe heat event. The models with temperature performed very well with R-squares of 94 or 95 cross-validated. Of course, when we first published these methods, reviewers were, you know, very harsh on us and, you know, demanded these different sensitivity analysis, looking at performances between states, between cities, rural versus urban, winter versus summer, but, you know, the model performed very well under the different scenarios. And of course, we extended these to other regions of the world. So we have a collaboration with Dr. Johanna Leopold from Grenoble, running these models in France. You can see the kind of model running over France, and you can see the spatial pattern of the high or the 1 kilometer predictions focused over Paris. Again, performance was excellent across France. And since then, we've also ran that in other regions, such as Israel and Italy. This is work by my former doctoral student, Dr. Francesca De Donato. And that's been fine, but we're also looking at ways of improving that. So one of the things that we've done, and this was also published a few weeks ago, work done by my student Ian Hugh, is using some of the machine learning approaches to go into deeper, high-resolution 200-meter temperature predictions, which is very important for the intra-urban variability of temperature. And what we did here, we developed a dynamic model, because temperature doesn't vary that much in rural areas, of course, depending on elevation and other kind of localized characteristics. But in general, you're more interested in variability within the city, but it's very costly to run these high-resolution models across a huge area such as France. So we developed these dynamic models that dynamically shift based on an algorithm we developed when it recognizes an urban area. So here we went deeper in terms of the daily resolution. We're talking about minimum, mean, and maximum temperature for 2000 to 2016. We predict 1 kilometer predictions based on weather stations, MODIS LST data, and additional covariates. And then we go down to this machine learning model in a 200-meter resolution across 103 areas or cities that we defined as urban areas. And I'll show you how we did that. We start with a similar calibration approach, which I've explained, giving us daily 1 kilometer prediction. This is then used to predict daily 1 kilometer resolution predictions across the whole area. And then we start with our machine learning dynamic shifting, where we use random forest and gradient boosting to predict 200-meter resolution data based on Landsat temperature, which is a higher resolution satellite data product, and high resolution NDVI. And then we ensemble them into an overall 200-meter prediction. These are the results over France. You can see the 1 kilometer model. And this is the 200-meter model. And you can see the differences within the urban area of France between the coarse 1 kilometer data and the 200-meter data. Performance was also great. We are moving towards hourly data in terms of temperature. So in this case, in Israel, we're also imputing LST data based on a machine learning model that takes into account ECMWF and Severi data, and we're generating these hourly 1 kilometer predictions over Israel. In this case, again, we took ERA5 ECMF metrology data. We took the Severi satellite, which is a geostationary satellite, giving us LST on a 4 kilometer resolution, allowing us to reconstruct daily surfaces. I thought I had an example here, but allowing us to reconstruct daily surfaces of LST imputed data from MODIS, again, to allow us to have more computationally efficient models. And this is the example I was talking about. This is an example of a MODIS LST product where we impute and create these daily surfaces. We're doing it very well with a root mean square prediction of 0.65, so we have a lot of confidence in this imputation. And this leads us towards our random forest approach to predict hourly temperature readings across Israel for every day, for every point across the whole time frame. So I saw the slide that I have 5 more minutes, and I want to leave enough time for Kevin Lane, a good friend. So I'll briefly go over some of the other stuff that are not necessarily satellite related that we're doing. We have a noise estimation model, that we developed. Unfortunately, we can't use satellite to measure noise. As far as I know, there aren't any satellites that do that, so we have to go back to caveman methods of using normal regressions. And we we conducted a preliminary analysis of noise across Israel. We published that a few years ago. We used a land use regression methodology looking at 2 major cities in Israel, Tel Aviv and Beersheba, and took a out-of-sample validation area adjacent to Tel Aviv. We conducted a 1.5-year measurement campaign, taking random measurements at random points across the different time periods and seasons, and developed a model incorporating a lot of the traffic and GIS-based variables such as traffic volume, junctions, land use, parcel classifications, and so on, resulting in a model. This is the location of the measurement points, and this is the final result of the model over the different areas. And the model, as you see, cross-validated, performed quite well. Extension of this, and really exciting work done by Dr. Laura McGuinn, is going to enhance this over Mexico City. So she's conducting a noise measurement campaign now in Mexico City. We're going to enhance that with a lot of additional spatiotemporal new predictors and a lot of innovative approaches to link that, or link the predicted noise data to participants as part of the progress study looking at mental health, sleep quality, body mass index, and cortisol rhythms. We're also in parallel, in collaboration with Laura and Dr. Homero Harari, conducting a preliminary study validating noise sensors, specifically the Apple Watch, and we're going to compare that to traditional gold standard devices that we've used to measure noise, and also cell phone with Bluetooth devices, and COTS devices, which are small, cheap, off-the-shelf commercial devices, and see how robustly we can monitor noise using Apple Watches. Also, we plan on developing an application platform to collect real-time environmental data as part of this sub-project. We also do light at night projects. This is a light at night composite map that my student created from VIIRS. You've heard about the VIIRS satellite. This is a light that we created, a light at night map that we created from DMSP data, which is an older satellite with a more coarse resolution. So we created this from 1997. And this is a light at night map that we created for 3 million years ago. It's a joke, of course, but that's how it would look because the algorithms know how to take away non-anthropogenic activities such as wildfires and so on. So it would literally look like this. We're using DMSP and VIIRS satellite data. This is an example, by the way, of the VIIRS light at night imagery and the satellite zoomed over Beersheba. We have made contact with a lot of major municipalities in Israel, allowing us to build a very rich data set of illumination sources, such as the height of the light lamps, the wattage, the type of illumination, and we've worked with the light or illumination engineers to convert that into luminance. Again, we're using land use regression methodologies, bringing in a lot of predictors having to do with building geometries, and different spatial and temporal predictors. And this is, initial results of cross-validated fits of the model and the model outputs around Beersheba in Israel. Of course, we do a lot of greenness or NDVI analysis using different satellites, and I think Kevin will discuss some of his work on that. We're developing accessibility measures, taking into account impedances. This is work in collaboration with Dr. Kevin Lane, or Professor Kevin Lane, taking into account the origin-destination matrices, but introducing spatial impedances, discussing how does crime, light at night, facilities, parking, how does that take into account your accessibility to different domains, such as education, facilities, green parks, health facilities, and so on. This is an example of some of the preliminary results looking at accessibility in Boston to educational facilities. And lastly, before I'm kind of kicked off the stage, we do a lot of location-based social network data. We've been mining Twitter and Flickr data for years now, and we've been using it in different studies. We've been scraping using the Twitter API. This is an example of tweets and density of tweets around Boston. And we're using established dictionaries to get at sentiment scores based on the tweets after we have cleaned the data, only left geolocated data. So you can see, like, your favorite president of all time is, someone is tweeting about him, and that results in a very negative sentiment score. And we've published on that on different studies using Flickr data to look at images. We're using the Microsoft and Google APIs for image classification. And I think I'll stop here. And thank you very much, and thank all my collaborators, which are a lot of my colleagues at Mount Sinai, at BU, at Harvard, and in Europe. Thank you very much.